Hi, and welcome back to Mr. Carroll's Classroom. Today we're talking about quadratic functions, and we have a special topic for you. It's completing the square. So let's go ahead and get started. Okay, so before we actually go over the method of completing the square, we need to know why we're doing it. So let's talk about the different forms for quadratic equations. So first we have the standard form, which is just ax squared plus bx plus c. And you guys should be fairly used to this. But then we also have transformation form, which is y is equal to a times the quantity x minus h squared plus k. So what are some of the differences here? And what are some of the similarities, and what are the benefits, and or the pros, and what are the cons? So first of all, similarities. So you should know that every single quadratic function, a parabola essentially, every single one can be shown in either standard form or transformation form. And really, completing the square is what allows you to go between these two forms. Okay? Now, as far as the benefits for each, let's talk about those. So for standard form, first of all, we can apply the quadratic formula, which students spend a lot of time memorizing and practicing. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a, right? So we can apply that with, as long as we have ax squared plus bx plus c, we can apply the quadratic formula to solve for the roots of the quadratic, which are the x-intercepts. So where does it cross the x-axis? We can also figure out the axis of symmetry fairly easy with the standard form. It is the line, the vertical line, x is equal to negative b over 2a. So that is going to give you the line that splits right between the parabola, whether it's facing upwards or downwards. The axis of symmetry is going to be negative b over 2a, which, by the way, you might notice from the quadratic formula, we have in the front negative b and then all over 2a. And so that does give you that that center line there, the axis of symmetry. And it's really the plus or minus the square root of all that stuff. That's kind of how we deviate from away from there, from that that center line. Anyways, let's see. Also, in standard form, if I have something in standard form, we have many different factoring methods that we learn and practice a lot to solve, and that's mostly so we don't have to apply the quadratic formula if it's not necessary, because it's so long. You can be prone to mistakes. So we like to factor to solve if we can, and then you can also list the y-intercept very easily in standard form. To get the y-intercept, you plug in 0 for x, and if I have ax squared plus bx, well, both of these terms are going to cancel out if x is 0, just leaving me with c. So that means that the y-intercept is always just 0 comma c. So there you go. There are some of the benefits. Not all of them, but those are some of the benefits of standard form. Now let's talk about transformation form. Transformation form, like most of these benefits, are going to revolve around graphing. And so in transformation form, I can graph, or you can graph, any parabola very, very easily just by looking at the form itself. You don't have to like plug in numbers or XY table or anything like that. It's simply, well, the vertex, and you can see here, that's one of the benefits. We know the vertex. The vertex is just h comma k, because h tells us how much it is shifted to the left and the right, and k tells us how much it is vertically shifted up and down. A will also tell us how much it is vertically stretched or compressed, and also whether it's pointing upwards or downwards if it's negative. However, let me backtrack with standard form. If the A is negative here, it's pointing down as well. If it's positive, it's pointing up as well. But so you really have that for both. Let's see here. You can also find the axis of symmetry very easily in transformation form. Since h is the amount that we're shifting horizontally, then it's simply the line x is equal to h. And then we can also apply the square root method to solve any quadratic that is in transformation form. It's also worth noting that transformation form is also called vertex form. So if you hear vertex form, it is transformation form for a quadratic. Okay, so what about completing the square? What does all of this have to do with completing the square? Well, when we apply this process of completing the square, we can take a quadratic from standard form into transformation form. So, and transformation form has the obvious benefits of a lot of graphing benefits. So very, very easy to graph. And you also really kind of get pretty much all the same stuff out of standard form, out of transformation form as you do out of standard form, but it's just graphing is kind of included. Okay? What we lose with transformation form are really all those factoring techniques. So anyways, so let's go ahead and talk about what it means to complete the square so we can go from standard form to transformation form. Okay, so let's remind ourselves of the goal. So when we complete the square, we want to take something from ax squared plus bx plus c over to this transformation form over here. Okay? So the method. I'm going to list out the method below here. There are 4 steps to this method, and I'm going to actually use 2 different examples to show you what's going on during this method. Because really, if you have this, in this first example, if you have a quadratic that is equal to 0, all you're really doing at this point in time is you're solving for the x-intercepts or the roots. But if you have, and I have the exact same quadratic here, if it's equal to y, that's really the equation of the quadratic itself, of the parabola, okay? So you can think of it equaling 0 as like a very specific case of when it's equal to y. It's only when y is equal to 0, or in other words, where it crosses the x-axis. So I would say that this one over here, if it's equal to y, that is much, much more flexible because it keeps the integrity of the original parabola, of the original quadratic. When we say it's equal to 0, then it's very easy for us to lose that integrity because we don't really care about like how much it's vertically stretched, for example. All we care about is where it's crossing the x-axis in this particular example. So anyways, so let's go ahead and talk about the steps. So step number 1 is going to be make room for the square. So we are completing the square here. So what in the world is this square? Well, we'll talk about that one in a second. We need to make room for the square. So what does that mean? Well, we are going to take away our constant term here. In this case, it's the minus 60. And we're just going to move it over to the other side of the equation. We're moving it out of the way because we want to put something in here, right? When we complete the square, we're actually going to add something into this equation, okay? And of course, we do it with both sides. Here, it's just 0 plus 60, right? It's just 60. But y plus 60 is just going to stay as y plus 60 over here. You will notice that completing the square is a little bit harder with when you have just y because, again, you have to keep that integrity of the parabola. Okay, so now that I made some room here, I'm actually going to put parentheses around this, we'll call it a trinomial, but there's really, I'm missing that third term from each one of these. And that's actually what we're going to add here when we complete the square. We're going to add something in here to make it nice, to make it work well for us. Okay? So next step is going to be if a is equal to 1, in this case, we have a 5x squared on both sides. If it's anything other than 1, we need to pull that out or divide by a. In this case, I'm pulling it out as a GCF. So if I go ahead and pull, let me grab my pen here. So if I go ahead and I pull this, pull this 5 out, let me grab a color you can actually see. If I'm pulling this 5 out as a GCF, I have to pull it from everything. Right? This third term is actually non-existent right now, so I'm just not pulling from there at all, and that's totally fine. You guys probably aren't used to doing that, but it is fine. It's just a blank spot right now. But I'm pulling that 5 out front, and over here, for the one on the left, I'm left with x squared minus 4, and I'm also left with x squared minus 4 over here because I just pulled out that 5 as a GCF. It's also worth noting if a is a negative number, you should pull the negative with it. Like if that was a negative 5, you should pull out a negative 5. Okay? Anyways, so now here is the part where we are going to complete the square. So what does that mean? It means we're going to add a value to both sides of the equation, because if I add something to the left, I have to add something to the right as well. So you're going to notice that I do that to both sides, but we have to be very careful to follow our algebraic rules. So before we even look at this, let's go down here and look at what I'm adding. So it's always the same. It's actually, you're going to add right here in this blank spot, you're going to add b divided by 2 squared. Now in this case, what is b divided by 2? Well, b divided by 2 is negative 4 divided by 2, which is negative 2. So I'm plugging in negative 2 squared. Now a lot of people will, and you might see this in books, where they put a 4 here, okay, instead of negative 2 squared. I don't like to actually put the 4 in there because this negative 2, you'll find out that it's actually like a really important number for our next step. So while the value is important, the value that negative 2 squared is 4 is important, this negative 2 is also important. So I'm going to leave it like that. Okay, so now, if I'm adding negative b, I'm sorry, not negative b, b over 2 squared, then I'm adding a value to the left-hand side, right? That means I have to add the exact same value to the right-hand side. This is where it gets a little tricky. You might think I added 4 here to the left-hand side of the equation, but actually, I didn't. I added more than 4. I added 4 times 5 out front. If I were to distribute this 5 back in, it would be 5 times 4, meaning I would have added 20. I actually added 20 to the left-hand side. So it's very, very important to know what number is out front. Don't forget about that GCF out there, because whatever you add inside of here, it actually gets multiplied by that thing on the outside. So I added negative 2 times negative 2 is 4 times 5. I add 20 to this side. So what do I have to do to the other side? I have to add 20 as well. And it's the exact same thing over here. I added 4 times 5, which is 20. So I had to add 20 to this side. Okay? That's really the most difficult part of completing the square. So you're making room to put in this like perfect number that's going to play really nice. Okay? And it's going to take us to our next step. This is where everything's going to fall into place. So the next step is going to be to factor this thing, actually. So, and when I say factor this thing, I'm talking about this guy right here, this trinomial. If I factored this, this is a perfect square trinomial. And so, and again, you could write it like this if you wanted to. If you put the 4 in there, it would be x squared minus 4x plus 4. And if I factored this thing, it would be x minus 2 times x minus 2. In other words, x minus 2 squared. Okay, and that's really important to us because that is getting us to the very close to the transformation form that we like. So when I factor this thing, it is x minus 2 squared. And by the way, this number here, this minus 2, it is always going to be the same as your b over 2. Okay, so that's why I prefer to leave it in that form, because then I just drop that that b over 2 down, which in this case is a negative 2. Okay. Anyways, this is going to be probably seem like a difficult process to you at first, but it's actually fairly easy as long as you practice it. It's actually, in my opinion, it's easier than the quadratic formula. You spend a lot more time learning the quadratic formula and memorizing that. Okay. So where are we now? Because that was really the last step of this. And I wanted to show you that under these two circumstances, one where it's equal to 0, which is basically saying, what are the roots of this? Where does this cross the x-axis? And the other one is equal to y, which is keeping the entire integrity of this parabola, not changing the shape of it at all. I want it to be exact as far as if I graphed this first one and then I graphed the final one, they should be the exact same. Anyways, so again, where does this bring us? Well, first of all, for this one, I have this this binomial squared times 5 is equal to 80. Well, I can actually solve for x there. I can solve for x by completing the square. And I'm going to go ahead and put these in here. So if I divided both sides by 5, I would have x minus 2 squared is equal to 16. Well, then I would go ahead and I would take the square root of both sides. Make sure you have a plus or minus in there. Trying to squeeze it in. But either way, you can then go ahead and solve for x fairly easily. And so this one over here, what is this one doing? Well, this is giving me y is equal to what? Well, y is equal to take a look at this. What form is this? 5 times the quantity of x minus 2 squared minus 80. That is our transformation form, okay? And could I solve for x here as well? Of course I could. I just say, well, instead of equaling y, it's equal to 0, right? When y is equal to 0, that gives me my x-intercepts. And then I would do pretty much the exact same thing as this. Add 80 to the other side, divide by 5, and I would end up at this exact same location over here. Okay? So there we go. I showed you the same method, completing the square, but in 2 very different ways. One of them was a simplified version of just solving for the x-intercepts. The other one was actually coming up with the equation over here in transformation form. Okay? All right. So let's go ahead and recap this really quickly. All right, so step 1, make room for the square. Okay, get rid of this minus 60, this constant term. Of course, you can't just remove it. You can move it to the other side, though, and make room for your perfect square. Step 2, go ahead and put parentheses around these, not to be confused, because you are going to put a third term in here. I guess that's not really step 3. That's just like an intermittent step. Step 2 is going to be to pull out a if a is not 1. Okay, in this case it was 5, so we needed to pull that 5 out as a GCF out of that trinomial. Then we are going to make this thing a perfect square trinomial by adding that perfect square in, which is b divided by 2 squared. It's always b divided by 2 squared. Okay? After that, we have transformed this guy into a perfect square trinomial, which we can then factor by listing it like this. And of course, all the numbers on the outside are just going to remain the same. But the whole point was to get this guy right here, that binomial squared. Okay? After that, you can basically do whatever you need to do at that point in time. In this case, over here, we would just solve for x by taking the square root of both sides. And over here, I don't know, maybe you graph this thing because it would be super easy to graph. Or maybe you go ahead and figure out the zeros by saying y is equal to 0, setting the whole thing equal to 0, whatever you want to do. Okay? All right, so let's go ahead and practice this because this is definitely a long procedure. Whoops. This is definitely a long procedure. And it takes practice to get it. Okay? So we'll start off with an easy one. And by the way, you can, in this case, let's see here, 3, 4, 2, 6. Yeah, you could solve this by factoring very, very easily, but that's not the point right now. Right now, we are trying to learn how to complete the square because this is going to come up more and more frequently as you go on in mathematics. In fact, when you're going to have an entire unit called conic sections and precalculus, and you're going to be completing the square all the time. So it really is an essential skill. And it is an alternative to the quadratic formula. If you really hate the quadratic formula, just go ahead and start completing the square. So, okay, so here we go. I guess I'll stick with my pink color here. Let's go ahead and we're going to do step 1, which is going to be make room. Okay, so I'm going to say x squared minus 8x. And I'm going to move that 12 over to the other side. Okay, so I've made room here to add a perfect square in. Okay, and I'm going to go ahead and put in my parentheses. Step 2 is going to be pull out a as a GCF if it's anything other than 1. Even if it is 1, you're pulling it out, right? But it's still the same thing, right? So anyway, so there we go. That step is taken care of because a is 1 in this case. In front of x squared, we have a 1. All right, next step here is going to be to add that perfect square. So let me go ahead and say plus, and that's going to be, remember, that is b divided by 2 squared. That's what we're adding here, okay? So let's go ahead and add that. So that's going to be plus b, which is, b divided by 2, negative 8 divided by 2 is negative 4 squared. All right, now, I just added something to the left-hand side of my equation. What do I need to add to the right-hand side? How much did I add to the left? Because I need to add that to the right. Well, in this case, I added negative 4 squared, which is 16, And out front is just 1, so it's just 16 times 1. So I added 16 to the left side, so I need to add 16 to the right side, right? Whatever I do to the left of the equation, I have to do it to the right. All right, now we're ready. Okay, let's go ahead and we are going to factor this thing. So this gets factored to x minus 4. And again, I could always just drop this down. I kind of use that as a shortcut. But if you don't want to use that as a shortcut, you could literally list this out as x squared minus 8x plus 16. And if you were to factor this thing, it would be x minus 4 times x minus 4, which is the same thing as x minus 4 squared. X minus 4 times itself. Okay, but anyways, so, but I like to use that little shortcut. Erase that. So anyway, so we have x minus 4 squared is equal to, and in this case I have negative 12 plus 16 is positive 4. And now, at this point in time, I'm going to continue to solve, because a problem like this would probably be asking me to solve for x. Since it's already equal to 0, that would make sense. So let's go ahead and solve. And we can, actually, I might even put like a little circle around this just to show you guys. That's a pretty terrible circle. Anyways, so like this is like kind of like, yes, we did it. We completed the square. But we're not done yet, right? Let's go ahead and solve this thing. So I am going to take the square root of both sides, because that is the opposite of something squared. So x minus 4 squared is equal to, and since I'm going to take the square root of an x squared, that I have to do plus or minus square root of 4. And this is going to drop out, so I have x minus 4 is equal to plus or minus square root of 4, which is 2. And we're going to go ahead and move the 4 to the other side, which is going to be 4 plus or minus 2. And let's go ahead and take each of our cases. So this means x is equal to, we'll make a set of solutions here. So let's do the minus first, since that's going to be like to the left on the number line, the lower number. So 4 minus 2 is positive 2. Or x could be 4 plus 2, which is 6. And there you go. There's your answer. We have solved by completing the square. We completed the square, then we went ahead and we used the square root method right here to solve. Okay, let's do another one. Make it a little bit harder. Okay, so here's our next example, and notice right away this is not in the form that we like, so let's go ahead and put it in the form that we like. And again, this could be factored fairly easily. Not all of these can be factored very easily, but I'm trying to give you more simple examples in the beginning here. So anyways, so let's go ahead and like for example, I could divide everything by 3 right now, right? But that's not the point, right? We want to practice the method of completing the square. So anyway, 3x squared, I'm going to add this 6x on this side. I'm going to make some room, and that's equal to 27 on this side when I add the 27 over. Okay? All right, now let's go ahead and we'll put our parentheses around here because we have this open spot for our perfect square. And I'll grab a different color. Let's grab pink. So I'm going to add, didn't leave myself a whole lot of room here, b divided by 2, which is 3 squared. Oh, shoot, I forgot. I totally skipped a step, didn't I? I never pulled out A. A is not 1. It is 3 in this case. So we need to pull that out as a GCF. Don't make the mistake. It's actually a very, very common mistake. As you can see, people look over that very often. So anyway, if I pull out a 3 as a GCF, that is x squared plus 2x and then plus something is equal to 27. And now we're ready. Let's go ahead and add our perfect square in here. So that is going to be, now b is 2. 2 divided by 2 is 1 squared. And now I just added how much to the left-hand side? Well, I added 1 squared, which is 1, but that is actually times 3. 1 times 3. So I actually added 3, a total of 3 to the left-hand side. So I need to add 3 to the right-hand side. All right, now we're good to go. Let's go ahead and we will factor this guy. So this is going to be 3 out front. Don't forget about that GCF. And this is going to be x plus 1 squared is equal to 30. And now I'm going to go ahead and divide both sides by 3, getting x plus 1 squared is equal to 10. And really, this is kind of like, yes, I did it. I completed the square. But we're going to continue, and we're going to actually solve for x, because more than likely, this type of problem is going to ask us to solve. Okay? Because it's not equal to y, essentially. All right. And by the way, yeah, it's not equal to 0 either, is it? Well, actually, it kind of is. If you went ahead and put this in standard form, it would be equal to 0 on one side. So anyways. All right, so let's go ahead and we're going to apply the square root method. So we're going to say the square root of x plus 1 squared is equal to, and again, I'm taking the square root of an x squared, so I have to say plus or minus the entire right-hand side, plus or minus the square root of 10. And here we go. The x plus 1 is going to drop out. And that's going to be equal to plus or minus the square root of 10. And can that be simplified? I do not believe so. We have, yeah, that's just square root of 10. 1 times 10, I'm thinking of the factors. 1 times 10 and 2 times 5. But none of those are perfect squares, so I cannot factor. Running out of room here, so let's go ahead and write our answer up here. So I'm going to subtract 1 from both sides. So that means x is equal to negative 1 plus or minus the square root of 10. And if you're wondering why I put that negative 1 in front instead of in the back, it's because whenever we have a radical or square root or cube root or any type of root, we typically put that at the end. Okay? So there we go. We have our solution. You could leave your solution like this. You could separate out the two cases if you wanted, but this is an exact solution, so I would preferably leave it like this. If you really wanted to separate it out and still continue to have an exact answer, it would be negative 1 minus square root of 10. That would be one answer. And the other answer would be negative 1 plus square root of 10 for the other case. Okay, giving those two solutions if you really wanted to separate that out. Okay? All right, I got one more example for you guys. Let's go ahead and try this one. So this one is definitely more difficult because I'm not actually going to solve. I'm just going to complete the square to put this into transformation form. If I wanted to solve, which maybe we will at the end, then I would simply just say, okay, well now y is going to be 0 because that's where the x-intercepts or the roots are. Okay, let's go ahead and apply our method. Now that we don't have 0 on one side, we have a y. Okay, and not much is going to change really. All right, so first of all, let's go ahead and make some room. So I'm going to say negative 5x squared minus 30x, and then plus a bunch of stuff, whatever, make some room, is equal to y, and I'm going to add this 365 over to the other side. So plus 365. All right. So I've got some room now. I need to go ahead and put in my parentheses because this is going to end up being 3 terms. But I need to go ahead and pull out a, which in this case is a negative 5. So I'm going to pull out a GCF of negative 5. So that means I have negative 5 times x squared. Now, when I pull out a negative 5 here, I'm left with positive 6x plus something, some kind of perfect square here, make some more room, is equal to y plus 365. Following all of my algebraic rules so far. All right, let's go ahead and add in that perfect square here. So what am I going to add? Well, it's going to be b divided by 2, which is 3 squared. Now, how much did I actually add to this side so that way I can add it over to the right-hand side? Well, I added 3 squared, which is 9, but then that's 9 times negative 5. So actually, I didn't add something. I subtracted 45. I added negative 45 to this side. So if I added negative 45 to the left, I can add negative 45 to the right, or in other words, just subtracting 45. Okay? All right, so let's continue on here. We're almost finished. We are going to factor this perfect square trinomial now. And don't forget about our negative 5 hanging out front there as a GCF. But when I factor this, it will be x plus 3 squared. And all of that is equal to y. And then I have 365 minus 45, so plus 320. And I really want to set this equal to y, so I'm going to go ahead and subtract that 320 off. So I'm going to say negative 5 times x plus 3 squared minus 320 is equal to y. And there we go. So this is the transformation form, or the form of y. Say y is equal to a times x minus h squared plus k, where h and k are your horizontal and vertical shifts, and also your actual vertex, the location of your vertex. And negative 5 says that this thing's going to be stretched out by 5, and the negative says it's going to be flipped downwards. So there's all kinds of clues to this. It's very advantageous to have a quadratic in transformation form. Okay. Now, let's continue, and I'm actually going to finish this off by figuring out what are the actual roots or the x-intercepts of this, now that I have it in transformation form. So that is simply where y is equal to 0. So this is negative 5 times x plus 3 squared minus 320 is equal to 0. All right? And let's go ahead and solve. So in this case, I have something nasty here. Let's go ahead and isolate that nasty thing. So we're going to say negative 5 times x plus 3 squared is equal to 320. Adding that 320 over. Now I'm going to divide by negative 5. So I'm going to say x plus 3 squared. And let's see, 320 divided by negative 5. What is that? 20 and 100, 60, 64, negative 64. Let me just double check that really quick. Make sure my mental math is correct. 320 divided by 5 is 64, so negative 64. All right, and let's go ahead and apply our square root method here. So I'm going to take the square root of both sides. It's going to be plus or minus, and notice I have the square root of a negative number here, so that's kind of interesting. We're going to have imaginary roots. All right, but anyways, so the x plus 3 will pop out of the left-hand side. And we are left with plus or minus the square root of negative 64, which the square root of negative 64 is the same thing as the square root of 64 times the square root of negative 1. And the square root of 64 is 8, and the square root of negative 1 is I. So there we go. Almost there. Subtract 3 from both sides. X is equal to negative 3 plus or minus 8i. And there we go. Those are our roots. And let me just check, make sure you guys can actually see that. Yes, my head is not covering it. Okay. All right, guys. So there you go. There is your introduction into completing the square. It is really an essential method to continuing your journey in algebra, specifically continuing going on into pre-calculus and beyond that. You will find yourself needing to complete the square more and more frequently as you go. And remember, it's also it is really kind of like an alternative actually to the quadratic formula. So if I had to choose which one to memorize or which one to become proficient at, which one would I choose? I don't know. It's hard to say. I think you should know both. But I do think completing the square has a slight edge over the quadratic formula because you get so much out of it. You don't just get your roots. You get this new form, which is super easy to graph. So in transformation, or also called the vertex form. So anyways, I hope this lesson was very helpful to you guys. And yeah, I'll see you guys in the next one. Have a good one. Bye now.